that works, and then to talk about how can we make like a ZKRollup based upon the EVM. So yeah, the idea of ZKRollup is that we want to have a proof of validity for all of the transactions that we're processing. And then we publish like the data that we need to reconstruct the state. And that's basically the ZKRollup idea, that we have like a way to do computation that's trusted, and we also have that's like trustless, and we also have like data availability guarantees where all the data is published, so anyone is able to like unilaterally withdraw at any time. Because in order to withdraw, you need to know the state of the system. This also, like the benefit of ZKRollup is also it allows us to build trustless bridges. That like when you have a bridge from one L1 to another, or from one L1 to a sidechain, you have to have a trusting bridge. There always has to be some authority that says this state on this sidechain or this L1 is correct. But because we have a validity proof, in ZKRollup we don't need to have that. We can just have, a bridge that's based upon like the validity proof of the state of the system. So those are the two benefits of ZKRollup. It means we can have trustless bridges. Okay, so let's talk about like a simple ZKRollup first, and we'll discuss. We'll just go through that in order to inform our discussions later today. Okay. So we're going to talk about our ZKP. And all the things we're going to talk about in the next while is going to be happening inside our ZKP. Like I said earlier, we need to make a proof of validity in order to be able to, in order to show that everything that's happening in our system is done correctly. So we make a proof of validity with our ZKP. So here's the things that we need to check inside our ZKP. Before we talk about that, let's talk about like what does our system look like. So all the time when we talk about ZKPs, at least for now, we have a ZKP. We have a Merkle tree. We have a Merkle tree is like an accumulator that has this very short representation of a huge amount of data. And this. Sorry. Is that good? Yeah, bigger too. Okay. And this is beneficial because like inside our ZKRollup we have like a lot of data, and we don't want to have to store that data on layer 1 because it's just a lot of data to store. So instead of storing it on layer 1, we store the like very short representation of this data, and that's called a Merkle root. And basically the way that we calculate the Merkle root, is that we make this kind of tree. This is called a Merkle tree. We have this tree where we have all of our users. There's Alice, Bob, Carol, and Denise. So each of these users has a leaf in the tree, and then we calculate the Merkle root by just hashing together these two things. So a hash function is this kind of like, it's this tool that takes like a big amount of data and converts it into a smaller amount of data. It kind of compresses that data. Yeah, that's what a hash function is. And the important thing about a hash function is it's collision resistant. That it's really hard to find like two input data that lead to the same output data. So anyway, we use a hash function in order to compress this big amount of data into a small amount of data, which is just the Merkle root. Okay, so how do we make our first validity proof? Well, the first thing that users need to do is they need to sort of consent to making a transaction. So let's say that Alice wants to send some money to Bob. So the first thing that Alice needs to do is Alice needs to sign the from address, the recipient, the to, and the amount. So Alice signs this and sends it to our coordinator. So let me draw this. So Alice sends a signature to our coordinator, who makes the ZKP. So what does the ZKP prove? So basically the ZKP, let me clean up a little bit here. So we have our signature. Alice sends it to the coordinator, and our coordinator is now going to make our zero knowledge proof. Our coordinator makes our zero knowledge proof. So basically we have a Merkle tree with Alice's leaf and Bob's leaf, and we have our signature. So the first thing that the coordinator does, or that the prover does, is check that the signature is correct. You need to verify the signature is correct. So they verify the signature is correct inside the ZKP. The second thing that they do is they look up the from, to, and amount. From the signature, they get the from. They get the from address. And the first thing they need to do is to make sure that Alice has enough money to transfer the money from Alice to Bob. Because if Alice wants to send like $100, we need to make sure that Alice's balance is more than $100. So the next thing that they do, so they get the from address, and then they do a Merkle, they need to like load this data. And with a Merkle tree, the way that we load data is with a Merkle proof. So they make a Merkle proof for Alice's leaf, for the from address. Yeah, and that basically gives us this value here. So the next thing that we need to do is we need to check that the amount is greater than the balance of Alice's leaf. So we basically do Alice.balance is greater than amount. Right? And like we're doing this check to make sure that Alice has enough money in order to be able to send it to Bob. And this, so like what happens if this proof fails? What happens if Alice doesn't have enough money to send to Bob? Well, if Alice doesn't have enough money, it's impossible for the prover to make this proof. It's just like this check has to be satisfied. If this check isn't satisfied, it's just impossible to progress. So like this is an interesting piece of nuance to recognize that like inside ZKRollups, when there's like a failure or an error, it's often the case that it's just impossible to proceed with the proof. Right, so we need to check the balance is correct, and if the balance is correct, then we need to reduce Alice's balance. So Alice's new balance has to equal the old balance minus the amount. So we've successfully processed about half of the transaction. We've taken Alice's leaf and we've subtracted away the money that she wants to send. And the next thing that we need to do is we need to save Alice's leaf. Now, like so far, we've only processed Alice's leaf in memory, right? We haven't updated the most important thing, which is our Merkle root. We've only kind of loaded this leaf and we did what we did. So the next thing we need to do is update Alice's leaf. So there's two important things that we have to achieve during this step. The first thing is that we need to change Alice's leaf. The second thing is that we need to change only Alice's leaf. We have to make sure that the prover isn't able to change other leaves in the tree. Right? Because there's an attack here, that if the prover is able to update the tree at more than one position, they're able to basically print money. Like the attack here would basically that like a malicious prover would update Alice's leaf but also update Bob's leaf at the same time, giving Bob like infinite money, or giving Bob like 100 million money, and then Bob would be able to withdraw and just steal that money from other people in the system. So like we want to have this invariant where like money can neither be created or destroyed. It just passes from one person to another. Right, so that's how this works. Yeah, so in order to achieve this, we need to look at how we did our Merkle proof. When we did our Merkle proof earlier, we got the from, but we also had this like witness data. So the witness data was basically a summary of the rest of the information in the tree. Just the way the root is a summary of all the information, the witness data ends up being a summary of the rest of the tree. For example, to make a Merkle proof that A is part of root, you basically give A and B and you hash them together. So what we do in order to keep Bob's leaf constant is that we use the same witness data. Right? Because like the witness data is a summary of the rest of the tree. Therefore, if we use the same witness data, then we end up keeping the rest of the tree constant, and we're only changing the single leaf Alice's leaf, the single leaf from Alice. So that's what we do. We update Alice's leaf with another proof. So we say the new root equals Alice's new leaf equals the Merkle proof of Alice's new leaf and the same witness from before. So now we've processed half of our first transaction. Basically we process half of our first transaction. Basically we take like we've taken Alice's leaf and we've subtracted the amount of money she wants to send to Bob away. Right, so any questions so far? Yes?
Yeah, so if you are going to update the whole tree, shouldn't there be, I would say, concurrency?
So the question is, if you're going to update the rest of the tree, shouldn't there be concurrency? So like basically what you're saying is that like you want us to like you're saying that, well, shouldn't we update Alice's leaf and Bob's leaf at the same time? Is that what you're saying?
No, I'm saying that suppose you have more than one coordinator, then you should have some conflicts between them, right? Because
right. So you're saying that like if you have more than one coordinator, there's going to be some conflicts between them.
Yes.
Yeah. Yeah, I think so. So in this case, we have a single coordinator. It's possible for us to have multiple coordinators and decentralize that role, but like we'll only ever have one of them making a block at a time. Just the same way that like with Ethereum, we have only one person making blocks at a time. There's only one miner who's making a block. And the mining process is basically the process of deciding who that is, who gets to make that block. That like, yeah.
All right, thanks.
Okay. Sorry, the mic.
So I would like to ask about the signatures here.
Yeah.
Does it contain everything like from fruit, apple, rather than amount, like that, right?
Yeah. So the signature is you sign the hash of to from amount. Like we're doing a symbol example here where you sign the hash of those things. But actually in reality you'll also have nonce. You'll have nonce here too. But like basically you sign the hash of this, and when you want to check the balance, for example, you do a similar thing to what you do when you do the Merkle proof. That like we have this like succinct representation of everything that was signed. And then when we want to look at the balance, we provide a proof that this balance is correct.
Okay. So the signature is from zkEVM or just a signature, normal signatures?
It's just a normal signature. So,
and the proof here, you write like proof of from and witness. So it means the ZK proof here, right?
Sorry, say again?
Proof of from and witness. So this proof is a ZK proof, right?
Oh, so the from is from the signature. Okay, let me put in blue the things that come from the signature. From, amount, then the witness is provided comes from it comes from the coordinator or the prover. The prover provides the witness as just a way of proving that the prover provides the witness so that the proof is able to like efficiently check that like this leaf is actually in the Merkle tree.
I see. So the proof means that from is in the Merkle tree, is in the leaf of the Merkle tree,
Yeah.
right?
Yeah.
But is it a ZK proof?
No, it's a Merkle proof.
I see. I see. No.
Yeah, I'm sorry. It's a Merkle proof. So let me update that so this is a Merkle proof. Merkle proof. And this is another Merkle proof. This is another Merkle proof. Okay, let me clean this a bit. Yeah.
I see. Thanks.
That good?
Okay, thanks.
Okay. Cool. Okay, any other questions? Great. So what's the next thing that we need to do? So we processed half of the transaction. We've updated Alice's leaf. We've reduced Alice's balance. So now it seems like the tree is kind of like missing some money. We've taken like the amount from Alice and we've kind of like, it's not in any leaf in the tree now. We've updated the root and it's kind of like the prover has some money in their hand. And like their responsibility is to give that to Bob because Bob is the recipient of this transaction. And like it's really important that like not only is the coordinator not able to steal from users, but also the coordinator is not able to like remove money from users. They're not able to like delete money. Like because there's a difference here. Like stealing money implies that you get it, you have an incentive to get it, but also like deleting money is still like a bad thing to be able to do because you can threaten people to like delete their money. You can extract some kind of like bribe from them or some protection money or something. So the next thing that we need to do is we need to take the money that the coordinator has taken so far and we have to force the coordinator to give that money to Bob. So let's go through that process. I'm gonna delete this part if that's okay and do the same process for Bob. Okay? Okay, so what's the next thing, what's the first thing that we need to do? Sorry?
From and to.
2, yeah. We need to do 2 to Bob. So how do we do the 2 part?
You get the 2 from the signature.
You get the 2 from the signature.
That from the
Yes?
signature.
Yeah? And then what do we do? So we have the 2 address from the signature. And what's the next thing that we need to do?
And then you get the proof.
Yeah. So we need to get the proof. So this is a Merkle proof. Merkle proof of what? Of what you said earlier, the 2?
2 and the witness.
2 and the witness. What color was I using for witness? Was that red? Yep.
Yeah.
Okay. Cool. So we got the Merkle proof of the 2 and the witness. What do we need to do next? So now we've kind of like loaded this into memory. We've taken the root and we've got like Bob's leaf. We have Bob's leaf and we need to update Bob's leaf. So what's the next thing that we need to do in order to update Bob's leaf?
With money to Bob.
Sorry?
Bob account is plus 2 amount.
Yeah, yeah. So let's do that. So it's like Bob.amount plus this like wait, that should be in black if I'm still following the same plan. So it's Bob.amount plus it's from the signature, it's amount, so it's blue. Perfect. Okay. So now we've calculated Bob's new leaf. So let's just call this like Bob underscore. Okay, so now we've calculated Bob's new leaf. So what's the next thing that we need to do? We got to update the Merkle root. And how do we make sure that we update just Bob's leaf in the Merkle root?
Okay.
So what we got to do is we got to use the same witness. Yeah. So we do that. So we say that the new root equals the Merkle proof of Bob's new leaf and the witness from before. Okay, and that's, what else do we need to do?
Make sure that the amount is the same.
Sorry?
Like the amount you remove from Alec and the amount you add into Bob is the same.
Right, yeah. So basically we do that by just copying the amount in the circuit. So like this is just coming directly from the signature. Well, yeah, you're right. So we need to make sure that this amount is the same. That's right. Is there anything else that we need to check?
No.
Nonce. So like in this example, we didn't talk about nonce. So the idea of a nonce is to provide replay protection. That like in this situation, the coordinator could make many proofs, taking money from Alice and giving money to Bob, and just repeat that until all of Alice's money is gone. And this is bad because Alice is only consenting to send like 10. But actually a malicious prover is able to leverage this to send many, many amounts. So basically the idea of a nonce is it's just a increasing number. And like basically when Alice does a send, we just make sure that that Alice's nonce is equal to the nonce of the signature. And after that transaction is processed, we increase Alice's nonce by 1. No. Cool. So anything else that we need to do? So I suppose that like one other thing we need to do is we need to set the public inputs of this ZKP, right? Because the ZKP doesn't operate by itself. It's actually operating between like it doesn't operate by itself. It's actually like used by the prover and by the prover, like the ZKP on its own is not a ZKRollup. We need to interface with a smart contract. And the smart contract needs to be aware of like some of the things that are happening inside the system. So like what kind of things does a smart contract need to be aware of?
The input, output, and the proof that the change during this process is correct.
Yeah, so you said that they need to be aware of the input and the output, and the change during this step is correct. Exactly. So what's the input?
For this particular transaction,
Yeah. Like what?
not in the signature.
This.
From to amount.
Right. So this is the data that we need to publish. So yes, let me put that on chain. So let's just have it. This is a public input. So it's from, it's to, and it's amount. What else do we need to pass as a public input? Sorry? The witness? No, the witness can be provided outside the system. Yes, the old and the new root. So we have the old root here, and we have the new root here at the end. The new root. So both of those are passed to the system. So what does the smart contract need to verify?
Wait, sorry. You don't need the nonce?
You don't need the nonce. You can compress the nonce out because the nonce is only ever increasing.
Right.
So if I see this to address, I can calculate the new nonce. Because I know the nonce of this account before, I just basically say, oh, Alice's nonce is going to be Alice's current nonce plus 1. And that's always going to be the case. The nonce is only ever going to increase like that. So like this is kind of like gives an intuition towards a whole set of optimizations that we can do. Like we talked about earlier or yesterday about how with layer 2, the only important thing to optimize for is call data. Because like our proofs are basically, our computation is basically free because we either have a ZKP, which is like constant cost for our computation, or we have a fraud proof, which will never be executed, or theoretically never be executed, because the incentives to create a fraud proof are just not there. So this is a really interesting like area of research in layer 2 about compressing the call data. Cool. Cool. So what does our smart contract need to check? Yep, we need to check that the ZKP is correct. Let me make some space to write this down. We need to make, we need to check our ZKP. What else? Yep, we need to check the root. What about the root?
Sorry?
We store the root.
Store root.
Yeah. Root equals root prime. And what else?
The root is the current one.
Yes, we have to check that this root is the current root. Okay, so I'm going to change the colors here a little bit. I'm going to have public inputs from smart contract to be red. Root prime. I'm going to have public inputs to be red, so I can have red here. Root prime. Okay, so also this is a equality check, and this is a variable change. Cool. What else do we need to check in the smart contract? Anything else? Yeah, I don't think that there's anything else either. I think that that's enough checks. I don't think we need to check anything else.
Do we need to store the new balance to the...
In the smart contract?
No, actually, the people use the call data to store that.
Yeah.
To recover
So this is call data, but call data doesn't really store. Okay, so sorry, let me just explain what call data is. So in Ethereum there is contract storage, and this is very, very expensive. To store a variable on chain costs a lot because you're basically asking every Ethereum node to store this variable in memory in the state, and that's just and that's really expensive because we need to keep the state small. Because the state it grows, it means that like your hard disk needs to be bigger. You need to download more data when you're verifying the chain. And like our philosophy is that like we want as many people as possible to be able to verify the state of Ethereum. So because of that, we try and limit the state as much as we try to limit the size of the state as much as possible. Yeah, because of that we try and so we make storage very expensive. But there's this other way of making sure that like data is available without without publishing it, and that's called like call data, or that's kind of like putting it in call data. And basically the idea is that like you just include these variables in the transaction, and you check them. You check that these are inputs to our ZKP, but we don't store them anywhere. And like the benefit of this is that like that makes sure that everyone knows these variables. Everyone knows what they are, but no one is able to but they're not stored. So we don't have this like overhead of like having to store these variables, having to get them and save them again in the state. Instead, we just have them as part of the transactions that you need to download and verify. The difference here is that like if you store something, you need to have it available all the time. If you put something in call data, you just need to have it available once, and then you can forget it. After you've verified that like this data is correct, you don't need to store it anymore. So like one of them is like read only, and the other is read write. So call data is read only, so it's a lot cheaper, and storage is read write, so it's a lot more expensive.
Do the call data have the system to recover from some issue? For example, like everybody lost the power supply, and then the network need to reboot or something. Do that help the network reboot?
Right. So the call data is used to make sure that an important role of this coordinator is to provide these witnesses. These witnesses are important to update the state, but they're also important for withdrawals. And like the issue is that if this coordinator disappears, the witnesses won't be available anymore. And if the witness isn't available anymore, everyone's money is stuck. No one is able to withdraw, no one is able to transfer. So we need to have a way to guarantee that this is going to be available. And the way that we guarantee that this data is available is by providing it in call data. And the idea is that like this is like really small amount of data to publish, but it allows you to reconstruct the whole tree, because you can just see that, oh, this is the state before, here's the list of accounts that were changed, here's how they were changed, and you just continue to update until you calculate the latest. Cool. Yeah.
So do we need to use the ZK property here?
We don't use the ZK property here. Yeah, that's an important thing to recognize, that like ZKRollup doesn't have any privacy guarantees. In fact, we're going out of our way to make it transparent. We're going out of our way to make it transparent by publishing the list of things that were changed. And like this is important because we want to have transparency so that people are able to continue the system, that we're building a system that's for scalability rather than for privacy. That said, we can make something called a ZKRollup, which has privacy as well. That's a little bit different, but it's a little bit different, but it's functionally Yeah, it's a little bit different, but using the exact same techniques, we can build a ZKRollup, except we have to replace the signature with a ZKP. So instead of having a signature, you just have a ZKP that like, you use a ZKP for privacy from the coordinator. Yeah.
So I think if people try to like cover the transaction with the knowledge proof, it may have some issue with the data availability.
Right. So the question is that like, if we try and make a ZKRollup, will we have some problem with the data availability? And the answer is yes, but we can adjust our system in order to overcome that. So let's think about like how Zcash works. So Zcash works by, we have a ZKP that some users spend their money, and we have something called a nullifier to prevent double spends, and we have the new leaf that they're updating in the tree. And when we have these three things, we're able to make a Zcash system. And like our data availability problems just depend upon publishing those three things. So we basically publish them. It's not going to be as scalable as this because the data you need to publish is bigger. Like that's like 256 bits for three things. Here, the to, from, and amount is going to be like, from is like 32 bits. If we have 2 to the 32 users, this is 32 bits. This is 32 bits, this is 32 bits. So that's 64, and that's 90 something. So like it's basically 2 transparent transactions for, yeah, okay, so it's like you can have 6 transparent transactions for 1 ZK transaction. Yeah. Cool. Any other questions?
Question? Yeah, so you mentioned that on-chain data availability is very important.
Yes.
So what do you think about Validium or the recent hybrid approach of Starkware, which is volition?
Is what?
Validium, when they don't have data on-chain,
right,
but keep only at the layer 2, and volition, in which they allows a hybrid approach for the user to choose whether to have data on-chain or just at layer 2.
Right, right. Okay, so I think that like having data availability at layer 2, okay, so let me talk about Validium first. So I think that Validium works, Validium is like less secure than ZKRollup. And the reason for that is that like you're trusting the coordinator to maintain the data. These two witnesses. These are important for being able to replace the coordinator and for withdrawals. If the coordinator doesn't have these, if this information isn't shared with other people, then the coordinator is able to like prevent people from withdrawing or delete people's money effectively. And like the ZKRollup prevents people from stealing money, but I feel like if someone has the power to remove your money, they can just insist upon having a very high fee in order for you to transfer your money. So I think that there will always be incentives for people to do that. The other way that I think about this is that like we want to build like censorship resistant systems. And if we build censorship, like this system is not censorship resistant, right? Because it's just a single coordinator. If that coordinator decides not to include transactions anymore, all the money is basically stuck. They're not able to do anything. The money is just basically sitting there. So like that's my problem with Validium. The hybrid approaches have the same problem where like you have to move, like the hybrid approaches have basically like if you're in Validium, you have the same problem where you're not able to withdraw by yourself and like the coordinator is able to like charge you a ridiculously high fee in order to transfer, or they're able to prevent you from withdrawing if they want to. Also, if they're like doing some censorship attack or forced to do some censorship attack, there's no way to recover. Like I think that the thing that's important about decentralization is that like you have neutrality and you're able to recover from states where the system fails. And in this case, with Validium, you're not able to do either. You don't have neutrality because there's like a single coordinator or a group of coordinators who have the data, and you're not able to recover from so you don't have like neutrality, and also you're not able to recover from states where they lose that data. There's no way for you to kind of get the latest state after that. So that's what I think about Validium. Yeah.
So in another word, it means that if you keep only data off chain, then it means that you only have something like semi-custody.
Yeah. Okay. If you keep data off chain, you don't really have custody of the funds. You're like trusting this other group to kind of maintain your funds for you.
Yeah, they cannot really spend your money, but they will be able to prevent you from spending it.
Yeah. Exactly. Yeah.
Okay. Thanks.
Yeah, sure. Any other questions?
So actually, like even the coordinator stopped working. So I think I can like bring myself to be myself can become a coordinator and then reconstruct it, and then I can withdraw my money.
Yeah. That is. So there's two things we need to be aware of when we're thinking about this. That like, in the worst case, we want users to be able to become the coordinator. And we need to think about like the leader election for the coordinator. Like, how is the coordinator able to make blocks? How do we decide who is making the blocks? Because we discussed earlier that like we need to have like a single person doing it at a time. So like there seems to be there's like two different approaches. One approach is that like you have a forced transaction where on layer 1 you say, I want you to include this transaction. And like when someone includes that transaction, they need to process it and continue. When you put that transaction on chain, the coordinator has to include that transaction. If they don't include that transaction, they won't be able to make other blocks. Like that's one approach that helps you. The issue with this approach is that it costs a lot to do the on-chain transaction. Like imagine a world where you have some very popular ZKRollup that has like 1 million users, and we're using like the future IP 4844 for data availability, so the transactions are really cheap. If those users want to make a transaction on layer 1, they just won't be able to. There's no way for 1 million users to make a transaction on layer 1. So we need to build systems where like the forced transaction is really, really cheap. The other thing that we need to do is, the other thing that we need to think about is the leader election. Like how do we decide who's able to make blocks? Like one natural idea here is to use proof of stake for leader election on layer 2s. But I don't think that proof of stake is a good solution for leader election on layer 2, because there's like on layer 1 it makes a lot of sense, because we have this issue of like if there's a censorship attack, we're able to have like a user activated soft fork to basically recover from the attack. And like in that case, yeah, we're able to have a user activated soft fork in order to recover. But like on layer 2, we're not able to do that. There's no way to have like a user activated soft fork on a layer 2 unless the layer 1 is also involved. And that's like trying to do that, trying to orchestrate that for a rollup that's broken seems to be very expensive and very difficult. So yeah, I think that like we have to be really careful when we think about leader election on layer 2. Like what you're saying does make sense, that like theoretically you could become the coordinator and make your own blocks, but we need to be careful when we think about building on layer 2. How is the leader election decided? How do we decide who's able to make blocks?
Yeah, so I'd like to have a question. So as we are approaching the merge, what do you think are the potential impacts of the merge to the ZKRollup ecosystem right now?
So I don't think there will be much impact at all. I think that the merge is, like there will be some nice benefits of having like more consistent transactions, and maybe we'll be able to have like get bigger, so like let me talk about that in a second. But like I think like the first order effects is basically nothing. I think there will be some second order effects that will help. Like one problem right now is that it's hard to make a transaction that's really big, that has really big call data. And when we're putting a lot of call data on chain, we want to have a transaction with a lot of call data. The reason that it's hard right now is that like the network is not really the network is not really optimized for broadcasting transactions or bigger transactions. There's this worry about the uncle rate because of the proof of work system is dependent upon transactions being broadcast across the network very quickly. So because of that, but that will change when we move to proof of work or proof of stake. There's some other interesting things, like we could reduce the call data cost for the same reason that, like, if we're not using miners anymore, we don't have to worry about so much about blocks propagating through the network as quickly as possible. But like, I think that our current approach is that after the merge, we're going to focus on 4844. IP 4844 is basically massive call data availability. So it should reduce the gas cost of call data a lot. It'll be slightly different than the current approach of just publishing on chain as part of a transaction. There will be a separate transaction type. But yeah, I think that that's that's the time when like ZK rollups and optimistic rollups are just gonna explode. I think that we can have like millions of users and thousands of transactions per second when we get there, and like that's one of the things where like Ethereum is like really, that's like, you know, that like people talk about Ethereum's functionality escape velocity, like what is the minimal set of features that we can have so that you can basically build anything. And like the one thing that's missing is like massive data availability. And once we have that, I think we'll be really close to being able to have rollups that have millions of users. And I think that we could get there now, but it would just be a little bit expensive. So I'm really excited for IP 4844. The merge is less interesting for ZK rollups or an optimistic rollups, but there will be some like second order benefits there.
Right, but you know, like with the recent event that DYDX is leaving Starkware because of the scalability problem that they claim.
Oh, I didn't hear about this.
Okay.
Yeah. So what is the issue there? Is the call data cost is too expensive?
Well, I think that they claim that 1,000 TPS is not good enough for them.
Right.
But as you say, we're going to reach like million.
Yeah.
So.
Yeah. So DYDX is like, okay, they're gonna move to
Site. They're their own chain.
Oh, right. Okay. Okay. Yeah, I did hear about this. Yeah. I don't know how much of that is just like, oh, I want to do another token, and how much of that is like really about the issues. Like, does DYDX consistently have more than 1,000 transactions per second requirements? Like, they're on Starknet right now. Is like, but is that the ZKRollup Starknet or is that the Validium Starknet? It seems.
Should be ZKRollup.
Okay. Okay, it's ZKRollup. Okay, interesting. Okay. Yeah, I don't know. I don't really know about this.
So.
What do you think about optimistic rollup and ZKRollup?
Sorry, could you say again?
What do you think about optimistic rollup
And ZKRollup.
and ZKRollup?
Yeah, I think they're both great. I think they're both complementary. And I think that like the systems that will eventually be like the most secure are systems that are combine the security of both. That you have a ZK rollup and an optimistic rollup that, yeah, you have a ZK rollup and an optimistic rollup that work, that like you have something that has the security of ZK rollup but also optimistic rollup. So you have a fraud proof and a validity proof. And like this will be really nice because it will let us, if there's a mistake in one of the proof systems, it's very unlikely that the same mistake will appear in the other. So it's like kind of how we have like multiple implementations of the EVM and the consensus layer clients. We have this sort of redundancy.
So it's like ZK optimistic rollup?
Yeah, yeah. We could have a combination of both, and I think that would be the thing that I would trust the most. Yeah. Yeah, so I think both are great. I think that like we have a lot to gain from working together.
I disagree. In current state, I use optimism and Arbitrum a lot, but I think they creating the fragmentation in liquidity. So I I don't think in this current state optimistic rollup is the future. So I really want zkRollup because for NFT or other currency, other token, if you want to transfer from the Arbitrum one, from Arbitrum to the Ethereum, it takes 8 days.
Yeah, that's true.
So
yeah,
it's very annoying.
that's true. That's true. Yeah, I hear you.
Yeah.
Yeah, that I definitely underweight the importance of liquidity. I think that like it'll be interesting to see ZK rollups in production and see, or EVM compatible ZK rollups in production and see like how they compete and like the different trade-offs and guarantees there. But like yeah, like what you're saying is compelling. Like that does seem like a limitation. But like I suppose that I was answering with like I just wanted to maximize security. But like maybe that's maybe not what you're trying to maximize here. That like we're trying to optimize for different things, and that's why we have like a slightly different answer.
So Barry, I heard that after the merge, you say that Ethereum will focus on lower the gas fee for core data. Yes, but and I heard also some proposal for some hash function that dedicated for ZKB, like rescue or Poseidon, and also some new curve, so some bigger curve for bigger secret of ZKB. So what are the state for the proposal? Will Ethereum have this soon, or maybe it allow a priority, maybe in far future?
Yeah, so like I think that like the first thing we're going to do. So right, so let me answer about the coal data gas cost reduction. So there's two approaches here. There's the like relatively conservative, just reduce the coal data gas cost. And there's the more radical, but also like much better, IP 4844, where we end up with like sharding and huge amount of data availability. So yeah, so I think that like, I hope that we can get to IP 4844 in the hard fork after the merge. I think that like we should prioritize that to the point where we just don't worry about anything else. I think that that's just such a huge priority that should just be our main focus. I hear you about the hash function standardization on Ethereum. I don't think that's going to happen anytime soon. Although I don't have any insider information. I'm not part of the core devs or any of those institutions. That's just my personal experience without having like discussed it a lot. I just know that I've been waiting for those types of things for a long time and they haven't really worked out. I think that like on our side, we're trying to focus on making efficient proofs for EVM friendly things like Ketchak and SHA-256. I think that that's like the solution that's like at least inside our control, that we're able to optimize those things. So like I think what you're getting at here is like the deposit cost for a ZK rollup that uses Poseidon or Rescue or something else is quite expensive, and you want to know when that cost is going to go down. So I think it's not going to go down. I think that we should architect our ZK rollups to use to use EVM friendly opcodes in order to avoid this.
Okay, thank you. Some another question about zkRollup. So the zkRollup is cheap because we can batch many transactions inside rollup. However, in the early phase of a new rollup, by example, the cost of they hardly can get enough of transaction to make a batch, and how does the premier rollup like ZK or Stockware had do with the ZKRollup?
Yeah, so that's a big problem, that like these systems work well when we have a lot of transactions per second, but like when you make a new one, it's often quite low transactions per second. So I think that like one of the approaches that people are taking is to try and make a zkEVM compatible rollup, because if you have that, then you're able to have like many transactions per second, or you're able to have like a bigger set of people because it can be anyone with a smart contract. That building like an application-specific ZK rollup can be hard to bootstrap, and like I've seen that with some of the application-specific ZK rollups. The Optimism and Arbitrum didn't have that problem so much. There's other things that we can do to mitigate as well. Like one thing we can do is have like this weaker economic finality, so that like when a user sends a transaction, we can basically say, okay, let's wait and include this transaction later. Let's wait and include this transaction later. Here's a guarantee that the transaction will be included, or else I'll lose $100 or whatever. Like that seems to be like decent enough UX that like it should still work, and then you just make a proof once per day or once every few hours. But like that is still kind of costly, and like bootstrapping rollups is something that's hard to do. You know.
Thank you so much.
Sure.
Any question? Có bạn nào có câu hỏi?
Okay, so let's do like 5 minutes about EVM and then take a break. Okay, so we talked about this and like how we can make a ZK rollup. The next thing that we want to think about is like, this is really simple, right? This is just transactions. We're just processing transactions, and that's all we're really processing. So, So how can we make a system that like does more? Because like we're worried about having enough critical mass to make our ZK rollup popular, and we're also worried about like how can we support more users or more applications. So it seems like a natural way to do it, to approach this, is to copy what the optimistic rollups are doing. The optimistic rollups are EVM compatible, and they've had like huge adoption. They don't have any issues with trying to get more people to build on top of them. So let's explore this idea and see how can we make a ZKP for the EVM. Before we do that, we need to think about, well, how does EVM work? Let's have a look and see. Is it, yeah. Okay, so like the EVM is basically like a stack machine where we have a whole bunch of opcodes. So we have a stack. So this is like a, sort of a temporary memory. I think the stack has like 1,024 elements. And basically, you have like 4 opcodes that can interact with the stack. There's push, pop, dup, and swap. So basically push, if you do like push 1, it basically just puts 1 on the top of the stack. If you do pop, it just basically takes the thing off the top of the stack and passes and returns it. So it'll just give 1 back. There's dup and swap. Dup is like duplicate 2 elements. And swap is take 2 elements and swap them. Let's not worry about dup and swap for now. Let's just keep it simple with push and pop. So that's the stack. And the other thing we have is like the bytecode. So the bytecode is basically just like a list of the opcodes. So we can have, let me do bytecode. So basically we have like push 0, pop, add, and Yeah, let's just have a program that does this. Oh no, so let me do a program that actually makes sense. So let's do push one, push two, add, pop. So how does this actually work? So basically we take the bytecode and we start at the top. We do them one at a time. So push one, that basically just puts one on the top of the stack. And then we finish that. We go to the next one. We say push two. Okay, so we push two, we put two on the top of the stack. Then we get to add. Basically what add does is it takes two things, it adds them together, and it puts the result on the top of the stack. So we need to take two things off the stack, 1 and 2, add them together, 3, push the result back on the top of the stack, 3. Finally, pop takes the thing off the top of the stack, 3. So that's it. That's our program. It just like takes things, adds them, puts things on. So this is the first layer of complexity. It seems like, okay, that's hard to do. Like we talked about before, about how like a user was like passing money around. It would take money away from Bob. It would give money to Alice. And like when we were doing that, we were doing Merkle proofs. And it seems like we could do Merkle proofs here too. Like we would just have the stack, and we would push one onto the stack. We would have a Merkle proof. We would update the root. And we would push two onto the stack. We would have a Merkle proof. We would update the root. And we would do this for like all of our different operations. Like the problem with doing this is that like it's expensive to do that much hashing, especially when we're doing it per opcode. So like let's look at the cost of these opcodes. Like these opcodes are all costing less than 5 gas. Less than 5 gas. And like an Ethereum block right now has 30 million gas. So 30 divided by 5 is like 6 million push, add, and pops. And that would mean that like if we were having a Merkle proof for each of those, we would have like, and this is 2001 to 24, we would have these really big Merkle proofs. It would just become like really prohibitively expensive. So it seems like the approaches that we've taken before can't really be applied to like the system that we have here. So any questions so far? Okay, let me introduce like the next layer of complexity. So we have our program here, but we also have like a whole bunch more opcodes that we need to deal with. For example, jump. Jump is quite tricky. So okay, let me write another bytecode that does the same thing, but is a little bit more complicated. So let me start here. So let's do push one. Push one. Okay, so we put 1 on the stack. Let's do push 3. So we're going to put 3 on the stack. Let's do jump. Jump is basically going to take, oh, wait. I mixed up the ordering. This should be, like when you put something on the stack, everything else moves down. So like I put 1 here, and then I put 3, but that's wrong. Because, yeah, so it should be on the top. So when I push 1 here, and when I want to put 3, I got to delete this one, put 1 here, and put 3 here. And that means that our Merkle tree approach that we talked about earlier won't work, right? Because if we have a Merkle tree of like, oh, here's 1, and we want to update it and put another thing on, we got to shift this one down. This one has to go here, and like 3 has to come here. And that's just really hard because we end up just shifting everything. Shifting everything inside a Merkle tree is going to be like at least a bit of work. Like we might be able to come up with some like clever way to do it where you just shift everything down and then you have like the left-hand side or whatever, but it might be hard. Anyway, so that just makes the Merkle tree a little bit more difficult. Okay, so we do push 1, push 3, then we do jump. So like, let's have like some other opcodes here. So I want to jump to 5. So let's have some other opcodes here. Push 2, push And let's add jump test. Then let's do push 10. Let's do push 2. Let's do add. And let's do pop. Okay, so what happens here? So we do push 1. This should be push 5. Push 1, push 5. So this is our current stack. Then we do jump. Basically what jump does is it says, okay, take the top thing on the stack and go to that index in the bytecode. So we have like index 0, 1, 2, 3. Okay, let me just start the index from 1. So 1, 2, 3, 4, 5, 6, 8. So this is the index. So we say, okay, let's just jump to that element. So we do that. We go, so we say jump to 5. Okay, so we come here. This is our program location. One of the rules of jump is that like you have to jump to a jump destination. So we're like, okay, fine, let's move here. Jump destination is correct. So we've removed 5 from the stack when we did the jump, because the jump will take an element off the stack and go to that location. And we went here. The next thing we need to do is make sure that like we did a jump. Let's make sure it's a jump test. Okay, that works. Let's move to here. Push 2. Okay, we got to push 2, which means we got to take 1 and move it down. 1 goes here, 2 goes here. So we're filling up our stack. Let's go to the next opcode. Let's go to add. So we take 2 elements off the stack and we put the result. We add them together. We put the result on the stack. So that's 3. And then we do a pop. We take 3 off the stack, and then we're done. So we do a pop. We take a 3 off the stack, and then we're done. So this is a little bit more difficult. So we talked about like, okay, we could potentially manage our stack by doing this kind of like jumps, or by doing the kind of Merkle tree, but it seems like it would be prohibitively expensive. So let's think about like how can we handle the bytecode? Like how can we handle this like jumping and stepping between? Like we could do the same thing with a Merkle tree. We could have like a Merkle tree with all of the different bytecode, and then when you update the index, you just go to that. When you update the index, you just go to that location in the Merkle tree. But that also seems to be prohibitively expensive, because each opcode is like can be like 1 gas, and if you're doing a Merkle proof for each gas, that's going to be really expensive in terms of prover time. So this is some of the reasons why the EVM is hard. Let me introduce the other 2 like tricky things. The other 2 tricky things is that we have like this is like temporary memory, and it's really short. It's like the cache, the L1 cache on your CPU. It's just like really small, and it's really cheap to access. It's really quick, but it's small, and you can't really do a lot of bigger calculations. So we have this M memory. Memory is much bigger, and we're able to insert more things into the memory. So memory is much bigger. And like another cool thing about memory is we can have like an index in the memory. We can just say, oh, store it at this location, store it at this location. So that's really nice. So it's like we have like a key value. Key value. And the other thing that like this is also like non-persistent storage. The other thing that we need to have is storage. This is persistent storage, which is like a Merkle tree, and it's a Merkle tree with Keccak hash function, and it's a really weird tree format. It's Merkle Patricia tree. It's not very common. It has a lot of like edge cases and things like that. But yeah, so this is Keccak. This is super expensive. This is super expensive and like very complicated to implement. The memory. The memory is also expensive, but it's not. It's similar to the stack. The stack and memory are pretty similar. So to interact with these, you have opcodes. Like we have mstore and sstore, mload and sload, just to interact with stack and storage. And yeah, this is basically all the stuff that's in the EVM that we, like, this is not all the stuff, but like for the purpose of this conversation, we can just limit the scope to this. The rest of the things can be solved using the same approaches. So like whenever someone writes a Solidity smart contract, they compile it, they produce the bytecode, and that's the bytecode here. Like every ERC20 token is just this stack. It's just like going through the stack, going through bytecode by bytecode. It's going through here. It's managing the stack. It's managing memory. It's managing storage. This is like how Ethereum smart contracts get executed. So like let's pause here, and like after the break, let's explore how we can make like ZKPs to like really implement this system. Cool. Any questions? Okay, let's have a break. Sorry? At what time should we finish at? Sure. Latest. Okay. Okay, so we already talked about like, can I use the back of this one? No, I can't. Okay. No, it's okay. It's all right. Okay, so we talked about like the EVM and how. So we started off talking about like ZKRollup and how to implement a ZKRollup, and then we talked about the EVM and why it's difficult to make a ZKRollup for it or a ZKP for it. So now let's talk about how we actually do it. So the first thing that we kind of did was to say, okay, let's just separate these things out. That it seems like we have a circuit. It seems like we want to do like 4 independent things: stack and memory, storage and bytecode. So let's just break them into like separate components. So let me clean up a little bit here. Okay, so we have 4 things we want to do. We want to do 1. Stack. Excuse me. 2 storage. 3 memory. 4 bytecode. So we want to do these 4 things. Let me clean up a bit and we'll talk about one at a time. Also, I want to merge these 2 together because they're very similar. Memory and stack are very similar, so we can talk about those 2 together. So let's talk about those first. So let me write up a little example. So we have our bytecode here. So we have our bytecode where we start at like 0. This is our index. 0, 1, 2, 3. We're doing storage, or we're doing stack, so let's do push 1, push 2, pop 1, pop, and pop. Okay, so let's look at what this looks like on the memory side. So on the stack side. So on the stack, we basically have index 1 equals 1, and then we have index 1. So that's when we push the value. We push the first one onto the stack, and index 1 becomes 1. And then we say, okay, we're going to push 2 on, so then index 1 becomes 2, and index 2 becomes 1, right? Because basically what we're doing is that we have our stack here. Where we have so stack, when we do push 1, we just put 1 here. Then when we do push 2, we have to take this one out, put this one down in the second position, and put this one here in the first position. So basically we can convert Oh, but wait, let me do the rest of the steps. So then we do a pop. So pop means that index 1 will become 1, and index 2 will become 0, right? Because when we do the pop, so we had our stack that was like 2, 1. So we do a pop, which basically means we take 2 out, and then we have to move 1 up to the position to the index 1, and that's the next step of the stack. Cool, and then we do another pop, which basically means we remove 1 from here. So how does that look in our transcript? Well, then we just basically say that index 1 equals 1. So like this is hard to do because like we're basically, when we're adding something to the stack, we end up having to change a whole bunch of different locations in memory. Yeah, we end up having to edit every single other location on the stack. So hold on, let me think for one moment. Yeah, I'm not sure. I think we might have a more efficient way to do the stack, but like let's just continue with this approach, and like we'll discuss it, and like we might have a more efficient version that's slightly different, but this is still the way that we do memory. Okay, so like the next step here is to say that like there's 2 things that are hard here. The first thing that is hard is that like when you put something onto the stack, it kind of affects everything else. The second thing that is hard is that like the order in which these things happen is undefined at setup time, because this is like a smart contract. Anyone can deploy a smart contract that does this thing in a different order. So basically what we say is we add another column here, and we basically say we have index, but let's add another column that's like timestamp. So this is the index, this is value, and this is timestamp. Right? So like the timestamp is basically the time at which it happened. So we say, okay, at timestamp 0 this happened, at timestamp 0 this happened. No, at timestamp 1 this happened. So that's timestamp 0 is this. Timestamp 1 is push 2. So these 2 happen at timestamp 1. And at timestamp 2, these 2 happened. So this is 2, and this is 3. So the final thing that we do to make this easy is that we reorder everything. At the moment, things are ordered by like timestamp, but what we want to do is order them by index and then by timestamp. So we want to have all the index 1 stuff together, and we want to have all the index 2 stuff together. So let's do that reordering and see. So let me do that in blue for the reorder. So we're going to do our reorder. Reorder of index, value, timestamp. Okay, so let's start with index 1. So index 1, value 1 is 0. 0. Index 1, timestamp 1 is 2. And what goes next? Next goes index 1, value 1, timestamp 2. And what comes next? Index 1, value 1, timestamp 3. So can someone tell me how to do the next part for index 2? So basically what we're doing is we're just ordering things by like the index instead of by the timestamp. So 211, 202. Yes, exactly.
Timestamp 3 is the value will be 0 for the index. For the index 1, 103, I think.
103, let me see. Yeah, you might be right. Oh, here. Yeah, this one should be 0. Yeah, that's right. This one should be 0, and that means that this one should also be 0. Okay. Okay, let's notice one thing here. That equals that. That equals that. Oh, wait. Sorry, no. That's not the right thing to notice. Push, pop. Okay. Wait, value 2. So basically, when you reorder like this, the value is supposed to be, oh yeah, whenever you do a push, the value just gets set to whatever you want. Whenever you do a push, you can just set the value to whatever you want. So let's mark the pushes. So push 1 is here. Push 2 is here. This is a pop. No, wait. Push 1, push 2. Yeah, this is a... Yeah, right. So this is only pushes, right? Yeah, okay. I see. So let me describe this a little bit better. So when you do, like, okay, so we have this new ordering. We have this new ordering where like things are a little bit easier to compute. The things that are easier to compute is like push and pop become really easy. Because when you do a push, you just take the timestamp and you just change the value at that timestamp. And when you do a pop, you just take the value of the previous timestamp and you use that. So this means that like the push and the pop become like just looking backwards. Yeah, it's just looking backwards or updating the current value. So because of this, we're able to make a circuit that like does our stack storage and memory for just like one row per edit, per element. And we do this by like reordering things. The one thing to think about here is that like, well, we're reordering things, but how do we make our circuits talk to each other? That like, it seems that like we have all of these different circuits, and like we just talked about like stack and effectively memory, but like the bytecode circuit needs to be able to take the output from these two things and include that in the latest computation. So wait, let me slow down a little bit. So for the stack and the memory circuits, does this make sense? Do people have some questions?
So for the memory, this can be like the index can be allocated dynamically.
Yeah.
So it's going to different content.
Right. So for the memory, sorry, let me repeat your question. For the memory, the index can be allocated dynamically, and like, how do we deal with that here? So basically, that's true, and the way that we deal with that here is that like, we just create another index for whatever address is allocated randomly, and like, or that is allocated dynamically. So if this is 1 here, but this could easily be like 52 or whatever. This could be just any location.
Okay, but what if the memory be reallocated for another application?
Right. So so the question is like, what if the memory gets reallocated for another thing? So that's fine. I mean, the memory is getting reallocated here as well, right? Because like when we're doing the extra push, we're kind of moving things down on the stack. Like when we do this first push, we put 1 into index 0, and then when we do the second push, we're kind of reallocating index 0 to have 2 instead of 1.
I see that there are one last problem with this. Is it the location where people put the free pointer to the like data, like maybe zeros, is zero, is 40, the address that holding the free pointer.
Right. Okay, so what's the definition of the free pointer? Is that like the next place to put memory?
Yeah.
Okay, so that's handled in the bytecode circuit. So let's talk about that. So we have so this is how we're doing the stack and memory. So what does it look like here when we say do push 1? So, oops. So let's take this as an example. So let's make a bytecode circuit that's very simple. Oops. Okay. Okay, so let's do a bytecode circuit. Okay, so basically we have our index, our bytecode index, which is 0, 1, 2, 3, our opcode, and our opcode. Okay, so this is push 1, this is push 2, this is pop, and this is pop. Okay. Let's do that. Right. So the other thing that we have is we have our stack table. So our stack table has the timestamp, the index, and the value. So our timestamp is just like this number that's increasing for every opcode. Our index is the location in memory, and our value is the value. So let's go through this and see. So the first thing that we need to remember is that the stack table is created by the stack circuit, and the stack table is kind of passed to the bytecode circuit to be verified afterwards. So the stack table basically is this, right? It's just like for different indexes, you have, for different timestamps, you have different values. So if I want to do push 1, I just basically look up index 1. So if I want to do push 1 at timestamp 0, I basically look up this table and make sure that the value is 1. Right? So when I'm doing this push operation, I get my timestamp, which is 0. I get my index, which is also 0. And then I get my value. And the value is 1. So I put the value 1. And then what I do is I just make sure that this is in this table. And if these values are in this table, it means that when we did this circuit, that was the value that was inserted here. So it's kind of like an API call to another location. Questions? I'm going to get to the question about the dynamic memory, or to the free pointer location in a second. Okay, so basically another way to think about this is that this is like an API. That we have one circuit, and that circuit's responsibility is to handle the stack. And we have another circuit, and that circuit's responsibility is to handle the bytecode. Independently, they don't prove anything. But once you verify, you have both proofs, they verify that the stack and the bytecode have been working together and that have been calculated correctly. The reason that they need to be calculated together or verified together is that they just cover different parts, and they need to have communication in order to be able to verify everything. So we tell our prover, you just make a proof about the stack, and that proof can be whatever you want right now. We're not gonna check anything. But later, if you want to combine that proof with the proof about the bytecode, it needs to be consistent with what we're going to do there. We're not going to check that right now, but we're going to check that soon. So we tell our prover to make the first proof, and then later we kind of consume that proof in another proof. We look at different results of that proof and say that, oh, this is correct. Because this is the value that we wanted to have here. We wanted to push 1 to index 0. So you're asking about the free pointer. So if we wanted to have like a free pointer, if we wanted to remember the last place in memory that's not adjusted, it seems like there's two places we could do that. One thing we could do, like, is the free pointer just like always increasing? Whenever you just add a value, you just increment it, and when you pop a value, you just decrement it? Okay, so if that's the case, what we could do is we could just do it as part of the push and the pop opcode. That like the first thing the push or pop opcode would verify these values in the stack table. And the second thing it would do was increment in the case of push, and decrement in the case of pop, the free memory index, or the free memory pointer.
So actually for the free pointer, the compiler going to take care of it when every time I'm write the code, and it going to like store a new value after I'm try to free that memory, like it's using the M store to the free pointer to store the new free memory address index.
Right. So that's handled by the compiler. But do we need to worry about a prover trying to store things to like not the free pointer location? Like it seems like that's one of the things that like, so let me just give the context that you're working on like a WASM, a proof of validity for WASM. And like in WASM, I think that like if a malicious prover is able to write to like not the free pointer, or if they're able to write to an incorrect memory index, that could be an issue. Yeah. So in that case, we need to force them to always and only to write to the free memory index. Maybe. I'm not sure 100% about the case of WASM, but there is definitely a bunch of edge cases that we deal with where we try and make sure that they don't write, we try and limit where they write things. That like, for example, if we didn't make sure, like for example, we have a stack pointer, right? We need to remember what the current bottom of the stack, or like how many elements are included, for a couple of reasons. One reason is that we can't have more than 1,024 elements, and another reason is that like, for a couple of reasons. One is we can't have more than 1,024 elements, and another reason is that like, we need to know where to go next. Like if someone tries to push like more than 1,024 elements, there's this weird error case that we need to think about. So anyway, for that we track the current stack pointer, and we say this is the current stack pointer to make sure that like the prover doesn't kind of overflow. That like when we think about proofs of validity, we're really careful about the error cases, because like if the error cases don't match like Ethereum's error cases, or if the error handling doesn't match Ethereum's error handling, it can be a little bit tricky to, yeah, it can be a little bit tricky. It can lead to cases where we're not 100% Ethereum compatible, which might lead to attacks. Yeah, it might lead to someone being able to make like a smart contract fail in a way that it wouldn't fail with the EVM. Like one benefit of using the EVM as the virtual machine is that you inherit, you kind of copy across all of the security guarantees of the EVM, or the security patterns that are used there. That changing the EVM could result in patterns that are different. Or like, for example, if I have a smart contract that works on Ethereum and I try and deploy it on some zkEVM rollup, then it can result in like a bunch of different issues related to, yeah, then it can result in a bunch of different issues related to, yeah, like if that contract then gets hacked, that's bad, right? We want to have the security guarantees the same as much as possible. So that's why we try and support the error cases. Cool, okay. Let me check the time. Cool. Any other questions about this part? So like basically the intuition here is that like by reordering things and separating it into two separate circuits, we end up being able to have like memory be super cheap, memory and storage. Okay, so let me clear this one and then I'll talk about like how the different components kind of come together. So we have our bytecode. So we already talked about how our bytecode circuit and our stack circuit talk to each other. And they talk to each other via this kind of like lookup table. So what else needs to talk to what else? So we have our storage. Our storage needs to talk to our bytecode circuit as well, because our storage is where like all of our storage values come from, but it's also where we load the actual bytecode from. So we have another connection between the bytecode circuit and the storage circuit, and our memory circuit has to go to storage and bytecode too. So our memory circuit goes to storage. Another thing that like we've implemented and need to connect to two different circuits is the Ketchak circuit. So Ketchak circuit is basically just like doing a lot of hashing. And we need to connect Ketchak to the storage as well as to the bytecode circuit, because like the storage circuit ends up doing like some Merkle-Patricia tree proofs, and that means that we just connect the Ketchak circuit there too. Also, the bytecode circuit will like process. It needs to perform Ketchak operations, so because of that, we kind of connect the Ketchak circuit there. Then we have some other circuits. Like we kind of then wrap this in a big aggregation circuit, because this is many circuits. We kind of just wrap this together in aggregation. We wrap this all together because we need to have like a succinct verifier. At the moment, the verifier is a little bit more expensive because, like, if we were to verify all of these proofs independently, it would cost a lot of gas. Because, like, number one, they have a lot of columns, and number two, it's just a lot of proofs. So the verifier is quite expensive. So we have an aggregation circuit to kind of merge them all together. Once we merge them all together, we're able to like verify them pretty efficiently. Yeah.
You have mentioned that we can treat the memory in the way that we treat the stack. So that's why we not combine the stack and memory circuits together.
Yeah. Like that's one reason. The other reason is that in the EVM, you're able to do two different types of memory operations. You're able to do mstore, but you're also able to do mstore 8, where you store 8 bits in memory. And that adds another couple of constraints, because we like basically in the memory circuit we need to break everything into 8-bit operations. We store everything as an 8-bit word, but in the stack we don't need to do that. But I think that at the moment we have merged the memory circuit together with the stack circuit and like half of the storage circuit.
So actually for that reason, the stacky also have the like the push one, and
The what?
I mean the opcode push one, because there are many kind of push opcode.
Oh yeah, there's push one, push, yeah, exactly. Oh, right. Yeah, that's true. So like, yeah. So we end up having to do, right, but like the issue, like the difference is, okay, so sorry, let me just explain. So like, when we were talking earlier, we talked about push and pop and like simple stack opcodes, but it's not actually as simple as that, because there's push one, push two, there's like push 32, where you're pushing like different like numbers of bytes onto the stack. And like the memory opcode has a similar pattern where you can do mstore, but you can also do mstore 8, where like in one case you're pushing 256 bits onto the stack, in the other case you're pushing like 8 bits onto the, you're storing 256 bits in memory, but in the other case you're storing 8 bits in memory. So like the difference is that with mstore 8, you're able to like insert into the middle of a bigger word. Like if this is like 0, 0, 1 and this is 1, 2, 3, 9, you can do mstore 8 in the middle of an index. You can do on-aligned inserts. But with push 1 through 8, it's not on-aligned. You just have like an element on the stack that like, oh, this is 256 bits. And this word is like 8 bits. But they both go on the stack as like independent words. So you're never like merging words together, but like with mstore 8, you're merging things together. And because of that, we basically had to break it down into like 8 bits. That's what we did at the start. We broke it down into 8 bits. But like in the longer term, we'll probably, yeah, we broke it down into 8-bit words. But in the longer term, we'll probably change that so that we can do online memory in the circuit. The reason for that is that mstore 8 is just really, it's really cheap, and it causes our mstore to be really expensive in terms of like the numbers of rows. So we're working on like a spec for the on-aligned memory in the memory circuit, and that should reduce our gas costs a lot. Cool. Any other questions? Okay, so let's talk about, so in the original section we talked about the public inputs at the start. So let's say we have a ZKRollup that's based upon the zkEVM proof. So what are the public inputs that we need?
Like the public inputs for this service. Like we did the previous, like we need the previous stage.
Yep.
Of the smart contract, and also we need the input from the transaction, and then maybe we also need the context of the caller, like the current state of EVM.
Okay, so what's a good representation of the current EVM state?
Maybe the, I'm not sure about this.
Like, could we use something like the state root?
Okay.
Okay. State root, and we also need to have the new state root.
Yeah.
And then we have the list of transactions we've included. What else do we need to include?
In the proof, you say?
Yeah, so like, okay, the context here is that like we're making a ZKRollup with the zkEVM. What are the other public inputs we need to pass from like the layer 1 contract to the layer 2 circuit? The bytecode? Yeah. Oops. Right, but the bytecode comes from the storage, which comes from the state root.
Then maybe some interconnection, maybe from layer 1, layer 2 to layer 1. So withdraw and deposit, something like that.
Ah,
Yes.
okay, that's an interesting idea. So the way that we handle deposit and withdrawal is we have a very simple message bridge. So the message bridge basically sends the layer 1 state root. And this is enough to look up anything that's happening on layer 1. So in order to build like a deposit and a withdrawal, what we do is, let me clean this a little bit and I can draw it. Okay, so we have here layer 1. This is our layer 1, and we have a deposit contract. And this is our layer 2. And we have a deposit contract here as well. Okay. And then basically what we do is we use our message bridge to allow this contract to talk to this one. So basically when a user wants to deposit money, they send a transaction to the deposit contract, which updates the values in the deposit contract to store a deposit at a certain location in the storage. And then they come to the layer 2 and they provide a Merkle proof that for the deposit contract, at this location in storage, there's a new deposit. And that allows the deposit contract to basically take the user's, that allows the deposit contract to unlock the deposited money. So when we create the deposit contract, we basically initialize it with like infinite Ethereum and infinite ERC20 tokens. And basically, anytime you make a deposit on layer 1, you use the message bridge to talk to layer 2. The advantage of this approach is it makes the creation of deposit contracts completely trustless. You can make like whatever deposit contract you want, and the discussion and like the communication between the different layers is relatively easy to do. Yeah, so we need our message bridge, but the message bridge is only the layer 1 state root. Cool. Okay, any other questions about this? Okay, let's finish there. Thank you everybody for coming. Also, I'd like to say thank you to Quinn for organizing everything and making all this happen. Thank you, Quinn.
Okay, so hi everyone. So let's wrap up the 4th workshop continuously from Saigon to Hanoi. 4 days continuously, 2 days in Saigon and 2 days in Hanoi. So I see like some of you also like join both workshop in Hanoi and in Saigon, right? And then what did we learn in the first workshop in Saigon? The first day, like we do the meetup with like DEP Vietnam community, and also like sharing about Ethereum projects, and also like about zkEVM, right? And the second day we study about Plum tutorial implementing Plum on Python, right? And 2 days in Hanoi, what did we learn? Yesterday we learned about Mercy, about Quadric, fundraising, And also today we learn about ZKRollup and zkEVM. So we thank you, Barry, very much. Like spending the time with like Dev Vietnam community, with Eat Vietnam, and like sharing a lot of like knowledge with us. And especially we can learn from the expert. And also like thank you for Kaiba team also like supporting us, and also like like co-host for the last minute like workshop in Hanoi. Thank you for all of you to joining the workshop online and offline. So we're also looking for your feedback. I think that like with your feedback we also can do the better next coming workshop. So can you scan the QR code? It just take only 1 minute to do it. Also like for whoever joining the workshop online live stream, please like scan the QR code now. Or if you want to give some feedback for now, like we also would love to hear from you. Or also like whatever you want to share with us or with Barry or with Ethereum Foundation. Yeah. Do you have any? Chưa. Any one of you want to share anything about feedback our workshop in Hanoi, in Ho Chi Minh City, so we also can know like what we can improve and do better. And then also like if you can do online also like this scan this. So this is only 5 questions. We would like to understand like before you join the workshop and after you join the workshop. So can you just like have to do it 1 minute? Okay. And also like after this workshop, we also do many others like weekly and monthly workshop online and offline. So if you want to looking for more information about the workshop under Eat Vietnam weekly, please scan the QR code over there. So also can check the information on the Eat Vietnam website. And we do the main event in November 25th to 27th. So also like after the workshop, also can join the hackathon and also can join the event. So let's keep in touch, enjoy the community of Eat Vietnam, and then we also like can share other information from the mentor and ask questions. Thank you very much. Okay, thank you. Let's have lunch.
Yep.